Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss about a module role of analytical chemistry under the paper Fundamentals of Analytical Chemistry. In this module you will learn about nature of analytical chemistry. You will learn how analytical chemistry grow, that is the growth of analytical chemistry, and also here you will learn what are qualitative and quantitative methods of analysis, and also analytical problems and their solution. All these things you will learn in this module. Analytical chemistry is as old Analytical chemistry is old as chemistry itself. In many respects, analytical chemistry acts as a foundation for other branches of chemistry. By using various principles of analytical chemistry, a complex material on analysis, a complex material can be analyzed, which on analysis give rise to a number of new and simpler constituents. An element as a substance which cannot be broken down into something simpler by ordinary chemical analysis arose from analytical data on different substances. The construction of chemical balance provided a quantitative aspect to chemical analysis. To study The study of analytical chemistry stimulated quantitative approach to various problems of chemistry. Chemical reactions were studied on the basis of quantitative and also quantitative. Chemical reactions were studied on the basis of qualitative as well as on the basis of quantitative changes. Induction of analytical approach brought about a revolutionary transformation from magic and alchemy to quantitative scientific chemistry. Because earlier times it was considered, alchemists, some alchemists used to consider that certain magic is there, certain philosophical stone is there, certain paras stone is there, which can convert iron into gold. By taking these things, by taking you, they have done number of experiments, and they used to do various types of magics for converting one substance to another. But they laid the foundation stone of modern chemistry, where different types of experiment started, and from alchemy we have come now to a stage where modern instrumentation is being used. At present, analytical chemistry plays a decisive role in the control of technological processes and becomes one of the sciences bringing a particular contribution both to the production of goods required by modern society and to scientific research. The important contribution of chemistry to the scientific and technical revolution of the last decade leads implicitly to the development of analytical chemistry too as an indispensable instrument both in scientific research and in the raw materials processing industry in general and chemical technology in particular. Modern analytical systems based on the introduction of apparatus working directly in production process plants as well as on the use of automatic equipment for laboratory analysis have created conditions of rapid and excellent control of the carrying on of technological processes, starting from the raw materials and continuing to the final products throughout all the manufacturing stages. It is characteristic of modern analytical chemistry that the elaboration of new methods of analysis implies a more and more active participation, in addition to chemists, of skilled men from the most varied branches of science, physicists, mathematicians, electronics experts, cyberneticians, etc. Analytical chemistry is also characterized by its ever close ties both with fundamental and applied research and with commercial production. Some years ago, our well-known scientist C.D. Nanitsu gave the following appreciation of the role of analytical chemistry. According to him, analytical chemistry is the universal and infallible control of every production process in any field of chemical industry itself, also in metallurgy, in the fuel industry, in metropolitan or industrial plants for water supply, in agriculture, in medicine, etc. The quality and to some extent the quantity of our output, the efficiency of our technological equipment, our health, all depend upon the accuracy and promptitude of analytical control effected at the appropriate time. The modern trend in applied sciences to turn wholly to profit in a complex way our raw material resources in order to obtain new products of especially high grade and often of high purity has also demanded an increased contribution from analytical chemistry. The particular merit of this discipline is to have risen theoretically and practically to the level of modern scientific and technological requirements, resulting largely in increased quality and quantity of contemporary production. Nature of analytical chemistry. Structural information about a complex compound can be obtained either by preparing it from some simple constituents or by breaking it chemically into smaller and smaller units and then identifying them. The former approach involves synthesis of the compound, while the latter is termed chemical analysis. Chemical analysis is broadly classified as inorganic or organic, depending upon the nature of the material under examination. Elemental analysis deals with the detection and determination of various elements present in a compound. Functional group analysis involves the determination of certain groupings of atoms such as carboxylic group COH or hydroxyl group OH in an organic material. It may be noted here that there is a difference between determination and analysis. Determination usually refers to the measurement of a single constituent in a relatively simple specimen, such as determination of barium in a given solution of barium chloride. Analysis is referred to a more detailed and complete process, which may involve collection of material, preparation of sample solution, identification of its various constituents, planning to determine these constituents, keeping in view the composition of the material, separation of the interfering substances, and selection of suitable methods for determining different constituents. For example, the analysis of a specimen of a rock or an ore. That is, determination may be a single constituent may be determined. It is a shortcut. It is a determination of a given substance, whereas in analysis is a total problem which starts from the collection of the material or sampling to final determination of all the constituents of a given material. According to some authors, the term estimation implies a rough measurement and they prefer to use the term determination. A major constituent is one whose amount is 1% or more of the sample material. A minor constituent present in quantities smaller than 0.01% is called a trace constituent. Chemical analysis is said to be complete when it involves the determination of all the components detected qualitatively in the sample. The analysis is partial when it aims at determining only one or a few of the components of the sample, such as determination of copper in a copper ore. So, overall analysis may be divided into two types. First was the classical chemical analysis, and another is the instrumental methods of analysis. Classical chemical analysis started with the application of techniques of gravimetric procedures. In a gravimetric determination, a known volume of sample solution is treated with an excess of a suitable reagent which quantitatively precipitates the desired constituent present in the sample solution. The precipitate, which is of known concentration, is filtered, washed, dried, and weighed. Knowing the weight of the precipitate, the amount of the desired constituent in the test solution is calculated. For example, an excess of dilute sulfuric acid is added to a given solution containing barium ions. The precipitated barium sulfate is filtered, washed, dried, and weighed. From the weight of barium sulfate, the quantity of barium in the given solution is calculated. Because such determinations are based on the measurement of weight, these are referred to as gravimetric determinations. In electrogravimetric analysis, the constituent to be determined is deposited on the electrode by passing electric current through a suitable electrolytic cell. For example, the amount of copper in a given copper sulfate solution can be determined by passing current through the solution and weighing the copper deposited at the negative electrode. And here, electric current acts as a precipitating agent. Gravimetric determination of a whole volatile constituent can be done by heating the sample and recording the loss of weight. Gravimetric procedures are quite accurate but are lengthy and tedious. Quantitative analysis was achieved by measuring volume of solution, hence it was called volumetric. Volumetric because we are taking here a certain amount of volume and titrating it. Volume and metric means measurement. In this type of analysis, sample solution of unknown concentration, a reagent solution of known concentration, is gradually added till the reaction between them is just complete as shown by some indicator. Volume of the sample and reagent solutions are known. The concentration of the reagent solution is also known, so that the concentration of the given sample solution can be calculated by applying the formula N1V1 is equal to N2V2. For example, volume of sodium hydroxide solution added is recorded, and from this the concentration of given hydrochloric acid is calculated. This process is called titration, and the determination is termed titrimetric determination. Earlier, such processes were called as volumetric procedures. So, volumetric and titrimetric procedures are one and the same things. Measurement of volume of the liberated gas can be used as a basis for determining substances producing the gas. Such analytical procedures are called gasometric methods. A particular component of a gaseous mixture can be absorbed in a suitable absorbent. The decrease in volume of the gaseous mixture gives the volume of constituent absorbed. This method of analysis is called as gas analysis, and this is very important because in analyzing air, finding out different constituents, this type of analysis is very useful. Another type of quantitative analysis is gravimetric analysis. Gravimetric methods, along with titrimetric procedures, belong to classical methods of analysis. Titrimetric procedures are much simpler and convenient, as you have seen. In direct titrimetric method, sample solution is directly titrated with the reagent solution. The indirect procedure consists of adding a known excess of reagent and titrating back the unused reagent. Classification of methods of quantitative analysis. The methods of quantitative analysis can be classified from different points of view based on the nature of material under examination, the type of method employed, the amount of desired constituent in the sample material, and so on. So, on the basis of different types, it may be divided as nature of material analyzed, that is, the nature of matter analyzed may be inorganic, organic, or biochemical. A much used classification of quantitative analysis is non-instrumental and instrumental. The former includes gravimetric and titrimetric procedures, whereas the latter involves use of instruments such as calorimeter, a conductivimeter, or a potentiometer, and so on. Such a classification is not very much justified because even the so-called non-instrumental techniques such as titrimetry make use of balances, pipettes, graduated flasks, etc., which though simple but are certainly instruments. Another classification into classical and physicochemical methods of analysis is also not very sound theoretically, although it is quite useful for the sake of convenience. According to this classification, gravimetric and titrimetric methods are termed chemical methods, though they are based on the measurement of physical properties, that is, weight and volume. The methods of analysis based on such physical properties as potential, conductance, current, optical rotation, etc., are generally referred to as physicochemical methods. But it should be remembered that these so called physical methods involve many chemical operations and that the measurement of a physical property is merely one of the several steps of the analytical procedure. For example, the only difference between a potentiometric titration and an ordinary titration is that the former uses potential measurement rather than a visual indicator for the detection of endpoint. The classical chemical analysis, which consists of gravimetric and titrimetric methods, is also known as wet analysis. Sometimes this is referred to as an analysis based on matter-matter interaction, as it involves a reaction between a substance to be determined and another substance, that is a reagent. There are certain other procedures which are based on matter energy interaction, such as calorimetric determination, which involves passage of light, a form of energy through solution of the substance to be determined, which is a matter. The methods of quantitative analysis can also be classified on the basis of the size of the sample for a determination. The term macroanalysis is used when the determination involves zero point 0.1 gram or more of the sample. If the amount of the sample is approximately zero point zero 0.01 to zero point 0.1 gram, the method is called semi-micro, and for samples weighing zero point zero zero 0.001 to zero point zero 0.01 gram, the term micro method is used. Ultra micro analysis involves samples containing less than zero point zero zero 0.001 gram of material. Some authors have used the term sub-micro analysis also. Certain procedures have been described for analyzing quantities smaller than those handled in ultra micro analysis. This constitutes what is known as super micro analysis. Some authors classify quantitative methods of analysis into centigram, milligram, and microgram procedures. These are applicable to methods in which the weight of the substance to be determined is of the order of a centigram, milligram, or a microgram, respectively. According to another qualification, macro methods are those in which sample contains more than 2 milli equivalents of the material and zero point 0.1 normal solutions are employed in their determination. In semi-micro methods, the sample contains about 1 milli equivalent of substance and zero point zero 0.05 to zero point 0.1 normal solutions are used in its titrimetric determination. When the amount of the substance is around zero point 0.1 milli equivalent, the method used is called a micro method. This generally involves the use of zero point zero 0.01 normal reagent solutions. Growth of analytical chemistry, how the growth of analytical chemistry has taken place and why. A remarkable fact about the development of analytical chemistry is that workers in other branches such as inorganic, organic, biochemistry, etc., have also contributed significantly to its growth. The difference in approach is that whereas an analytical chemist have his main interest in the methods and technique themselves, other workers develop analytical procedures for their own specific problem. For example, a worker in the field of chemical kinetics is not primarily interested in various analytical methods and techniques, but may develop a method for quantitatively analyzing a substance whose concentration is to be determined in order to obtain the necessary kinetic data. On the other hand, main interest of an analytical chemist is in the development and improvement of an analytical procedure itself and in testing its reliability. He also studies the interference caused by the presence of other substances and attempt to modify the procedure so that such an interference can be eliminated. In the above discussion, you have seen I have frequently used analytical chemist and an analyst. It is necessary to distinguish between an analytical chemist and an analyst. An analytical chemist carefully chooses a chemical reaction and uses it for developing an analytical procedure taking into account various theoretical considerations. It is the duty of analytical chemists to understand all these things, to plan the experiment, to find out the best possible path, to find out the all types of uh, possibilities which have to take into account. Earlier, methods of quantitative analysis were those involving gravimetric procedures. Volumetric determinations were developed by Marguerite, who titrated ferrous iron with potassium permanganate. Both direct and indirect titrimetric procedures have been worked out for the quantitative analysis of wide variety of organic as well as inorganic compounds. So here I explained you analytical chemistry, whereas analysts work routine type of work. Whatever instructions is given to a person, all procedure is given, and he will give the result by following the procedure, and that is called as analyst. So that is the difference between an analytical chemist and an analyst. Over the last 50 years, there has been a growing tendency to make use of certain instruments to achieve quantitative analysis. The titrimetric methods are not basically changed from the standard procedures. The instruments simply act as substitute for an indicator. So, as I have told you, that there are various limitations of using colored indicators. So, with the advent of instrumental methods, now these instruments have replaced the indicators, and now instrument has various property being used in the instrument is applied as an indicator of the color change when the reaction is complete. Recently, with methods commonly known as the instrumental methods of analysis have been increasingly used, especially for industrial and commercial quantitative analysis. There are several reasons in favor of this. Most instrumental methods depend on calibration curve or calibration data. Solutions needed for this purpose are standardized by chemical methods. Many instrumental methods cannot give precision and accuracy that is readily obtained in most chemical methods. The cost of equipment for chemical analysis is within the reach of every chemical laboratory because such simple equipment as balances, pipettes, burettes, measuring flask, etc. are required. The physiochemical methods invariably involve costly equipment. The classical and physiochemical methods of quantitative analysis should be regarded as complementary because once an instrument to be used in quantitative analysis has been properly calibrated, it can be used with great advantage to achieve rapid analysis, and due to high sensitivity of physiochemical procedures, samples at microgram level can be handled. The advantage of microchemical methods are saving of time, labor, and material. Much of the work on vitamins, hormones, and other natural products could be done due to the development of microanalytical methods because many of the compounds were present in micro quantities. In about last 50 years, there has been increasing sophistication in all areas of chemistry, physics, and biological sciences. This created analytical problems which required use of sophisticated instrumentation for their solution. For example, in determining traces of impurities at parts per billion level or determining traces of pollutants in the atmosphere of industrial area. Next is to understand the analytical problems and their solutions. The solutions of all analytical problems, whether qualitative or quantitative, follow the same basic pattern. This may be described under several general headings. Choice of method. The selection of the method of analysis is a vital step in the solution of an analytical problem. A choice cannot be made until the overall problem is defined, and where possible, a decision should be taken by the client and the analyst in consultation. Inevitably, in the method selected, a compromise has to be reached between the sensitivity, precision, and accuracy desired of the results and the costs involved. For example, X-ray, fluorescence, spectrometry may provide rapid but rather imprecise quantitative results in a trace element problem. Atomic absorption photometry, on the other hand, will supply more precise data but at the expense of more time consuming chemical manipulations. Second step is sampling. Correct sampling is the cornerstone of reliable analysis. The analyst must decide in conjunction with technological colleagues how, where, and when a sample should be taken so as to be truly representative of the parameter that is to be measured. Next step is the preliminary sample treatment. For quantitative analysis, the amount of sample taken is usually measured by mass or volume. When a homogeneous sample already exists, it may be subdivided without further treatment. With many solids, such as ores, crushing, and mixing are prior requirements. The sample often needs additional preparation for analysis, such as drying, ignition, and dissolution. Next step is separation. A large proportion of analytical measurements is subject to interference from other constituents of the sample. Newer methods increasingly employ instrumental techniques to distinguish between analyte and interference signals. However, such distinction is not always possible, and sometimes a selective chemical reaction can be used to mask the interference. The final measurement is often the quickest and easiest of the seven, but can only be as reliable as the preceding stages. The fundamental necessity is a known proportionality between the magnitude of the measurement and the amount of analyte present. After that, method validation is done. It is pointless carrying out the analysis unless the results obtained are known to be meaningful. This can only be ensured by proper validation of the method before use and subsequent monitoring of its performance. The analysis of validated standards is the most satisfactory approach. Validated standards have been extensively analyzed by a variety of methods and an accepted value for the analyte obtained. A standard should be selected with a matrix similar to that of the sample. In order to ensure continued accurate analysis, standards must be reanalyzed at regular intervals. The assessment of results. Results obtained from an analysis must be assessed by the appropriate statistical methods and their meaning considered in the light of the original problem. This is the way how a sample can be analyzed starting from the validation of the data. Importance of analytical chemistry to various branches of sciences. Analytical chemistry finds wide applications not only in different branches of chemistry but also in other physical and biological sciences and in many fields of engineering. Geologists use analytical procedures for analyzing groundwater, minerals, rocks, ores, etc. In agriculture, chemical analysis is used to determine the composition of soil in the production of fertilizers, insecticides, and weed killers. Medical and biological research programs depend on chemical analysis, which provides useful information that enhances our understanding of vital processes and helps in developing medicines to cure various diseases. In order to safeguard public health, there is constant checking of food, drugs, cosmetics, water supplies, etc. And this is done in analytical laboratories. Waste disposals and the composition of air in industrial area are analyzed to know the extent of harm they would cause to public health so that necessary preventive steps can be taken. There is hardly a branch of national economy which does not make use of analytical techniques. Chemical analysis is important in controlling the quality of raw materials, intermediate, and finished products. Hence, to produce high quality products, it is essential to have analytical control at all the stages of technological processes. The sale of raw materials by suppliers and their purchase by users is by analysis. Metallurgical products are most essential materials of modern economy. The properties of alloys depend on its composition, which is established by analytical methods. So, students, today you have seen the role of analytical chemistry and find that analytical chemistry plays an important role in various fields of science, not only chemistry, but various fields of science. It may be study of natural product, it may be biotechnology, it may be the analysis of body fluids. Whatever analysis is there is being done by an analytical chemist. Analytical chemistry studies and uses instruments and methods used to separate, identify, and quantify matter. In practice, separation, identification, or quantification may constitute the entire analysis or be combined with another methods. Separation isolates analytes, quantitative analysis identified analytes, while quantitative analysis determines the numerical amount of concentration, and and all these things can be done by classical methods and also by instrumental method. But with the development of more and more sophisticated instruments, now most of the analysis are done with the help of modern instruments, and also there is a tendency to check the reactions taking place in industries in various reactors at every stage of the reaction by interfacing the instruments with the reactors. Thank you.